Good afternoon, good morning, good evening. My name is Sandrine Deglin, and I would like to welcome all of you to today's presentation on the philosophical and logical principle of causal reasoning. On behalf of HESI's Environmental Epidemiology Committee, I also would like to thank you for taking the time to join us. And before we begin, I would like to cover a few logistical details. So I want you to know that this webinar is being recorded and it will be posted on HESI's Environmental Epidemiology Committee webpage. Throughout the presentation, you'll be able to enter your questions in your control panel in the question box, which is, you can see here framed in red. And so our panelists will read your questions at the end after our speaker's presentation. If you have any question about HESI or about the activities of the Environmental Epidemiology Committee, please do not hesitate to send me an email or give me a call. I'd be happy to talk to you further about what we are doing with this committee. And finally, if you want some information about future webinars, it will be posted on our committee page, which you will find on the HESI website, hesiglobal.org. So a brief disclaimer. I want you to know that the views expressed by the speakers are those of the speakers only and do not necessarily reflect the views of HESI or of its members. So now I would like to welcome our speaker, Dr. George Maldonado, who is an associate professor at the University of Minnesota School of Public Health. Dr. Maldonado has a PhD in epidemiology from UCLA. His focus is in epidemiologic method, and he spends his time thinking about how we can do a better job of getting answers to causal questions from imperfect non-experimental studies, most human health studies being both imperfect and non-experimental. He is the founding editor-in-chief of Global Epidemiology. I'm going to give the floor to Dr. Maldonado. Dr. Maldonado, thank you for joining us today.
Thank you, Sandrine, for that introduction.
I'm going to give you control of the screen.
Okay. Okay, so you can see my screen, Sandrine?
Not yet, let me see. Now I can, yes.
Okay, so we're good to go.
Yes.
All right. Okay, so the title of my talk is Causal Reasoning in Epidemiology, Philosophy and Logic. Oh, I need to play. Okay, there we go. All right, let me begin with a couple quotations I encountered early in my career as an epidemiology methodologist. So years ago, I was reading a biography of the physicist Richard Feynman, and it said that he thought of science as confusion and doubt, a march through fog. And I found this to be a good description of how I have felt as a methodologist over the years. There's a lot of confusion and doubt, a lot of fog in epi-methodology. The second quotation, I was at a job talk seminar years ago, and the topic was something to do with methods for observational studies. And somebody in the audience stood up and they said something like this, that observational studies should be done behind closed doors with the lights out. So I think that's a pithy way of summarizing the difficulties of using observational studies to answer the types of causal questions we do in public health. But unfortunately, you know, we can't not do observational studies. Most of the public health questions we ask can't be studied with randomized trials, so we're stuck with observational studies. So I sometimes think of what I do, and I think about these two quotes, and I have over the years, and I sometimes think of what I do as trying to clear away some of the fog and trying to open the doors and trying to turn on the lights as I study this difficult question of how to answer causal questions with observational, non-randomized studies and imperfect ones at that. So what I'm going to do in this presentation, I'm going to share with you some of my thoughts about how I think we can clear away some of the fog, open the doors, and turn on the lights as we take on this difficult challenge of using non-randomized imperfect studies to answer the type of causal questions that we face often in public health. One thing I want to emphasize, you'll notice throughout this talk that I'm going to be talking not very much about statistics or statistical analysis. I think the foundations of causal reasoning are more philosophical than they are statistical. So today we will be spending our time talking about philosophical and logical issues and very little about statistical analysis. So as we all know, public health questions often require answers to causal questions. And I think that studies designed to inform these decisions should be approached as exercises in causal reasoning. And again, we'll be talking about fundamental principles. And what we're going to be talking about today is work that should be done before statistical analysis begins. So here's an outline of basically what I'm going to talk about today. And I will talk in more depth about each of these bullet items throughout the talk. So studies designed to answer causal questions should do this list of things. They should ask well-specified causal questions. They should approximate, given practical constraints, a perfect study, and the perfect study for a particular situation should follow directly from a clear definition of causal effect and a clear understanding of the philosophical and logical basis for that definition. Then the study should examine how it falls short of approximating the perfect study, adjust the study results for these shortcomings, and in the published manuscript, state assumptions made in the design, conduct, and analysis of the study, and discuss why the assumptions are believed to be plausible for the topic under study. So let's take a more in-depth look at each one of these items. So it's important to have a well-specified causal question. And the causal question includes the following components: a health outcome, what I call an exposure contrast, which is just the contrast in exposure, whose causal effect we're asking about. And of course, we need to specify how much exposure and also when the exposure occurred. A target time period, by that I mean the time period over which the outcome of interest is monitored to see whether and when it occurs. And sometimes I find when I teach these concepts that the concept of a target time period is a little squishy. And so I use this little anecdote to illustrate what a target time period is and the importance of it. So let's say a man falls off the roof of a 10-story building. He jumps off the roof of a 10-story building. You're sitting on the 5th floor balcony. And as the man goes by you, you shout to him, "How's it going?" And he says, "So far, so good." So what I'm illustrating here is that if, for example, the study of this one person, the effect of jumping off a 10-story building on the outcome of mortality, if your observation period is the time from when he jumps until the time he passes the 5th floor balcony, so far so good, there is no causal effect of jumping off a 10-story building on mortality during that time period. So it's important that our time period is one that is relevant and interesting. Other components of a well-specified causal question: Specify a target population, that's the population about which we ask our causal question, and a measure of causal effect, which is the form that the answer to our causal question will take. So when we talk about the components of a well-specified causal question, it brings up the point that I think is sometimes overlooked, is it points out why we might often expect different studies of basically the same exposure-disease relationship to have different questions, to have different answers. And so I often see in discussion sections of a paper, they'll say something like, well, the results of different studies of this topic are inconsistent. And often the discussion section will sort of seem like they're saying, well, we don't really understand why. Well, there are good reasons for why different studies of essentially the same topic would have different answers, different estimates of exposure disease associations. It could be, and the first thing I look at is, do the different studies look at different target populations with different characteristics, different age groups, age distributions, for example? Are they looking at different target time periods? Again, the squishy idea of a target time period, the observation time period. And often the exposure contrasts are not exactly the same. The exposure levels that they're comparing are often different, and the exposure timings are often different. So when you think about the components of a well-specified causal question, it makes you realize that it's really not that surprising when different studies show different values of a relative risk estimate, for example. So the next step in causal reasoning is to envision a perfect study. And this gold standard study design that you should envision, it should follow directly and naturally, actually, from a clear and explicit definition of causal effect, which I think follows from a clear and explicit philosophical and logical foundation for your definition of causal effect. So I think it's very important to envision this perfect study and to have a clear and preferably quantitative definition of causal effect, because it's difficult to estimate validly and precisely a quantity that's ill-defined. I love this quote from Yogi Berra that I saw posted up on the bulletin board of one of my favorite restaurants years ago. So Yogi Berra said, if you don't know where you're going, you might not get there. And during my career, during the 30-some years I've been a professor of epidemiology, it seems to me that oftentimes, especially in the earlier years when I first started out as an assistant professor, that we often don't have a clear idea of what exactly that we have been estimating, what the form of the effect measure is that we've been estimating. And also it's important to have a clear idea of this gold standard study that you are striving to design your study to look like, because I think, and we'll talk about this a little later, it's important to adjust your study estimates, your study results for study imperfections other than just confounding, which we typically tend to focus on in our analysis. But you can't, it's really difficult to adjust for study imperfections if you don't have an idea of what you're trying to adjust your study results to, what this gold standard study design should look like. So to envision this this perfect study, this gold standard study, the philosophy that's currently used, currently favored by many epidemiologists, is counterfactual reasoning. And I like the definition of counterfactuals, I like this definition that I saw on one of my favorite TV shows, The Big Bang Theory. So on season 4, episode 3, Amy Farrah Fowler defined counterfactuals as, we postulate an alternate world that differs from ours in one key aspect. And I love that definition. It's a really nice summary of what counterfactual reasoning is. And we don't have time today to spend a lot of time talking about counterfactual reasoning and the ins and outs of it, but that is a pithy summary of what counterfactuals are. Given counterfactual reasoning as your philosophical foundation for defining causal effect, the perfect study that follows from that is what I call a causal contrast thought experiment. And the measure of causal effect for that study design is what we call a causal contrast effect measure. So, given your philosophical foundation of counterfactual reasoning, and that leads to this perfect gold standard study of a causal contrast thought experiment, you want to approximate within practical constraints a causal contrast thought experiment if you're trying to answer causal questions and if your philosophical basis is counterfactual reasoning. So just really briefly, here's what a causal contrast thought experiment is. And again, we don't have a lot of time. I could do an entire webinar on this gold standard study design. But the basic idea is, if your target population is an exposed group, the disease frequency that you observe under their exposure is capital A1 number of cases divided by capital B1 denominator. Disease frequency is A1 over B1. This is factual. What would have happened if instead that exposed target population had not been exposed is counterfactual. But if you could see what would have happened in this alternate world where just one thing was different, the exposure level was they were unexposed, you would observe this, A0 over B0. And so your measure of causal effect would be some comparison of disease frequency if exposed and the disease frequency that you would have seen if instead that same group of people during that same target time period had not been exposed, A0 over B0. So what's nice about this causal contrast thought experiment is that it isolates the causal effect of the difference in exposure patterns from other factors that affect the outcome frequency. And the logic behind this comparison is that the only possible reason for a difference in outcome frequencies is the difference in exposure patterns. So there's this logical reason for believing that if you see a difference in exposure between the exposed and unexposed groups in this idealized world, you have isolated the effect of your exposure that you're studying from all other possible reasons for why there might have been a difference in exposure disease frequency. So just very briefly, how do you approximate in practical terms? How do you go about approximating this causal contrast thought experiment? Well, you specify a target population that corresponds to the study question. You realize that one or more disease frequencies are counterfactual, and then you need to choose substitutes for these counterfactual disease frequencies to minimize confounding. And then you sample subjects from your target and substitute populations in the study to minimize bias and maximize precision, minimize cost and time. And very briefly, we could have several webinars on this, but this is just a sort of a thumbnail sketch of how you would go about given this gold standard study design, how would you, these are the steps you would use to approximate this in real life. So the next step that I think is really important is to, so you do your study, and it's important to understand a study's imperfections and how the combined impact of these imperfections might affect the study results. And I have bolded and underlined the combined impact part because epidemiologists tend to think about different study problems sort of individually. We think about confounding, we think about non-random subject selection or participation. We talk about measurement error. We sometimes talk about model specification error, maybe not so much. But what we tend to do is we tend to talk about each one of these separately, and we especially do this with measurement error. And yeah, we can talk theoretically about the contribution of each of these to the total amount of error, but it's really the combined impact. It's the total amount of error due to all of these potential study imperfections that we're really interested in. And so it's not really very helpful to talk about, for example, well, you know, the effect of measurement error is to do this, but because measurement error and each of these don't act alone. And so it's important to think about the combined impact of these imperfections. I know that, you know, I guess with measurement error is really the one where we make the most, where we're most guilty of this, where we often talk about, well, you know, if you have a certain type of measurement error, in a simple case, it will cause your estimate to underestimate the true. Well, that's its contribution to the total. It is not the effect of, that is not what actually happens to your effect estimate, unless you have no other study errors, which almost never happens in epidemiology. So confounding, you know, I could do an entire webinar on confounding, but basically the definition of confounding based on counterfactual reasoning is something like this. So again, let's say that we have an exposed target population. We observe A1 over B1 as our outcome frequency, like a risk of disease. We wish we could observe the counterfactual, what would have happened if instead this exposed target population had not been exposed, but this is counterfactual. So we find another population usually that has this unexposed exposure pattern like this here, and we use this as a substitute for this when we calculate a measure of association. And so now with this data and this data, then our relative risk estimate, association estimate would be A1 over B1 divided by E0 over F0, when we wish we could have calculated A1 over B1 divided by A0 over B0. And that's the counterfactual reasoning definition of confounding. And I am teaching a PhD seminar on confounding and study design this semester. And one of the things that we started the semester with was realizing that there are several different definitions of confounding, and this is the counterfactual one. So if this isn't the way you think about confounding, well, you know, that's fine. There are other definitions. So confounding is a potential major source of error. Non-random subject selection or participation is another major source of error. And the way that works is after we have specified our target population and a substitute for the counterfactual, we might sample people into our study, or we might have missing data which causes us to exclude people from our data analysis, or we may have losses to follow up. There are all kinds of ways that people from the target and the substitute that we've chosen are not the people that actually end up in our data set. And so if these Greek letters are the sampling proportions from one cell to from the uppercase letter to the lowercase letter, we can use the lowercase letters to calculate, say, a relative risk estimate, and that will be an unbiased sampling design if the cross product ratio of these Greek letters is equal to 1. So we can use this to equal that if that is equal to 1. Again, just very, very briefly. Measurement error, again, I've said something about measurement error already. The key issue here is that there is no simple rule in most situations for judging whether the total error, that is the combined impact of measurement error, confounding, non-random subject selection, model specification error, which we'll talk about in a minute, random error, etc., results in an over or an underestimate of the true effect size. So let's stop talking about measurement error causes an underestimate of the relative risk and then taking our 1.2 and saying, well, it must be greater than 1.2. Measurement error doesn't work alone, but it's the total error that's important. And the final major source of error that I want to talk about is model specification error. And this is something that we epidemiologists, anyway, don't really talk much about, which is unfortunate. The idea here is that statistical modeling, in essence, is a process that combines your data with assumptions to yield a quantitative result that's a function of both. I love this quote from a 1986 paper by Robbins and Greenland that expresses this idea. They said that a statistical model is a mathematical expression for a set of assumed restrictions on the possible states of nature. I think that's an elegant way of stating the idea that a model combines your data with assumptions. So the problem is, or the issue is, that if the modeling assumptions, in other words, the assumed restrictions on the possible states of nature are correct, then that's great. Statistical modeling will yield a better answer to your study question than you would have gotten from just your data alone. Of course, assuming no other important sources of error. But the problem comes that if your modeling assumptions are incorrect, those incorrect assumptions that you're adding to your data can cause error in study results. So to express this idea of model specification error, I love this quote by Mark Twain. So it ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so. And so I take that and I change that a little bit. And what I tell my students is it's what gets you into trouble is what your analysis model thinks you know for sure about assumed restrictions on the possible states of nature that just ain't so. So you want to make sure you know what your analysis model thinks you know for sure. I mean, you specify a model and your model goes, oh, okay, chief, you've told me that the dose response is log linear and that and the model says, okay, boss, this is true. And so I am going to give you an estimate based on these assumptions that I assume you know what you're talking about. But often we don't we often don't pay careful attention to the assumptions that are implied by models, and often, especially with the more sophisticated models, there are assumptions that are hidden. And so I think often we don't appreciate what the hidden assumptions are, and often we are a little too casual in the way we use models, and we don't really pay much attention to the assumptions that are implied by them, and we should. So when I was a doctoral student 1,000 years ago, for some reason, I was struck by the fact that you know that that epidemiology studies tend to ignore study imperfections. I remember scratching my head as a student when we would read papers in these seminar classes, and we would talk about these papers, and there would be all these potential problems that were simply ignored, and that always bothered me. So and I think that's not a good way to go. So I think you should always adjust your study results to account for the imperfections of a study. And it's interesting that there is there is something called bias analysis, which is just this: the procedures for adjusting studies for things that we don't normally adjust for in a data analysis. We typically adjust for confounding. We don't always adjust for measurement error, almost never adjust for measurement error actually, or losses to follow up or missing data that's excluded from our analysis. So there's this procedure called bias analysis, and I'm wondering why bias analysis is separate from data analysis. I don't understand why data analysis doesn't also include adjustment for things like measurement error and other things other than confounding that we usually adjust for. And then study results depend on design and modeling assumptions. We've talked about modeling assumptions as well as on the study data. And when reporting study results, I think it's important to state these assumptions and to discuss why you believe them to be plausible for the topic under study. So I know this rarely occurs in published studies, and as a journal editor-in-chief, I'm really encouraging authors to give a lot more discussion of assumptions that they've made in designing, conducting and analyzing the study, and talk about why they believe that these assumptions are plausible for the topic under study. So what I've shared with you today is some suggestions for how I think we can clear away some of the fog, open the doors, and turn on the lights when trying to answer causal questions with imperfect observational studies. And I'll take questions now.
Thank you, Dr. Maldonado. So for our audience, if you would like to ask questions, you can type them in the question box.
I guess one, this is David Miller. I would just ask a question, I guess, before folks had started writing things in, because I don't see any yet. But why do you think there's less use of bias analysis, uncertainty analysis in epidemiology, and it's not an integral part of the data analysis? Any thoughts back on that?
Well, I mean, that's a good question. It certainly is not the tradition. It's not. It wasn't happening when I was a student, and you know, I don't know. It's just not a tradition. It is. Well, it's extra work, and methods for doing it are still being developed. So we don't have a fully worked out suite of methods for correcting for combinations of all of these errors. So, you know, there's methodological work still to be done. More research is needed. But I frankly don't really understand it. It seems like something that we should be doing. And yeah, good question. Fog. The reason for this is very foggy to me.
Okay. Okay, thanks. There's one actually. I'm trying to. Yeah, hold on for a sec. There's one question in on that. So let me scroll up. Your presentation leaves the impression that existing methods are available to do studies that assess causal questions. Why do you think these methods are not frequently used? Are there fields, particularly epidisciplines or economics, that are better at using them?
You know, I am interested in seeing how other disciplines approach these issues. I don't think, my impression is that other disciplines that try to use observational studies to answer causal questions aren't doing any better than we are. So yeah, so I don't know that anybody's doing a better job than we are.
Okay.
You know, the thing is that you know, this is a really hard problem, and I mean, people have been talking about causal reasoning and defining what is a cause and how to decide what is a cause for hundreds of years, and so it's a really difficult problem, and it's a very complicated one. You know, when we talk about, you know, sometimes people will talk about what do they call the really super hard problems? There's a term for that. This is one of the really super hard problems, I think, because causation is so complicated, and doing a study and the way things can go wrong in a study also are very complicated. So it's a very difficult thing to do that we're trying to do here, to use observational studies. There's just so many things that can go wrong, and there are so many non-causal associations for most exposure to disease relationships, and trying to untangle the causal ones from the many non-causal ones is just a really difficult problem.
Okay. Do you think? I guess actually, here's another question that just came in. Thanks for these insights. We participated in a HESI good practices seminar for epi studies for risk assessment. Do good practice guidelines exist for studies for publication purposes to minimize biases? or is this the reviewer's responsibility? So the good epidemiology practices for risk assessment, do they exist for minimizing biases?
You know, there are guidelines, and interestingly, I'm not really all that familiar with them. I have looked at them previously, but none of them seem to me to be to do a really good job of it, which is why I put together the manuscript that goes along with this paper. I think this is my list of good practices, and I don't know of any other good practices guideline that does anything like this, or that is that I think is sufficient.
Okay, thanks. And that manuscript should be available to folks under the handouts tab on the screen. Follow-up question. I don't see another one now, so I'll go ahead and ask this. DAGs are being directed acyclic graphs are becoming to be a little bit more popular, but they're still not widely used in epidemiology or environmental epidemiology.
Yeah.
They purport to get at the causal question. Any thoughts basically on why they aren't used more often, and what it would take basically to have them used more frequently? I'll give you just kind of an example. Oftentimes in EPA and off-specified programs, when we look at studies, they'll be looking at the same outcomes, for example, the same exposures, but different authors will choose to control or as confounders for different things. I mean, one author may choose 6, another author may choose 2 of those, and then 5 others or something like that. So it seems like DAGs would assist with that in terms of at least just kind of having the same set of information and thoughts together in terms of that. So any thoughts on DAGs, how they might help, and why, to the extent to what they might help, and why they're not more frequently used?
Yeah, that's a good question. So you know, what DAGs are supposed to do is they're supposed to give you a sufficient subset of variables to control, to adjust for in a model, to control for confounding. So a couple points about that. One is that my impression is that let's see, how can I state this? My impression is that when people talk about methods for causal inference, like using DAGs to control for confounding, my impression is that they forget about the fact that what I said today is that it's the combined impact of study problems, not just confounding, but the other things that that are important for getting a valid answer to a causal question. And I think the people that use DAGs, or the literature on DAGs, ignores the other potential problems. And so they're, in that respect, I think the use of DAGs is not sufficient for improving our answers to causal questions. So, and that's actually my criticism, or let's say my my observation of published papers that talk about methods for causal inference are almost always statistical methods for controlling for confounding, which is not sufficient for answering causal questions. You need to consider and adjust for these other problems. So DAGs, I don't consider a method for causal inference in and of themselves. Now, the other thing about DAGs is, I'll have to admit that, I mean, talking about confusion and fog, I seem to be one of the few people that seem to be very foggy on the use of DAGs. So you're catching me at, your question is catching me at a moment of extreme fog. whereas around me there seem to be a lot of people that really love DAGs and think that they are great. My confusion about DAGs is that thinking about how causes occur, I have realized, and I guess we all know this intuitively, is that no factor in and of itself causes disease by itself. It's always some kind of causal interaction between lots of factors within an individual. And so, and then in my thinking about confounding, I've realized that I think of confounding in terms of interactions of causal factors within individuals causing an individual's causal type. And so it's the distribution of causal types across different populations that determines if confounding occurs and whether and how much confounding occurs. The problem with DAGs, but my confusion about DAGs is that they don't consider the causal interaction of multiple factors together. DAGs are, nodes in a DAG are one variable at a time, and I don't understand my problem. I don't understand how causal diagrams that ignore causal interactions can identify confounding variables to control for when confounding is a function of distributions of causal types, not necessarily distributions of single variables. So fog, this is my fog.
Okay, thank you. Useful to know on that. So there's another question that's on there, but I'm going to just precede it with a thought from me on this. I mean, I come from a regulatory perspective, so we're definitely interested in causal relationships. I mean, just knowing there's an association between ice cream sales and shark attacks isn't good enough for us, basically, to make the determination that the government should regulate ice cream sales to minimize shark attacks on that. The question that has come in is this, and I kind of wondered your thoughts on that. Just knowing that there's a correlation can be equally helpful for drawing conclusions as knowing there is a causal relationship. Where do we really need to derive causal relationships from epidemiological data?
Well, I mean, here's the thing. If I am going to, or if policy is made, the idea is that if I'm going to make a change or a policy is promulgated to make a change in some environmental exposure, for example, the idea is that we want to make a change that's going to actually make a difference. And so if you make a change on a factor that's not causally associated, you're not likely to see an improvement in health. So to maximize our chances of improving the health and well-being, we should be intervening on causal factors. That's the bottom line.
Great. Okay. Thank you. Another question is, I'll read this one. I don't know if Igor is on and might have any questions of his own to ask. But when thinking about how epi is understood, interpreted, and criticized by other disciplines, for example, where the science is more experimental than observational, do you think as epidemiologists we need to focus more on the methods and making sure we are being as rigorous as possible with our methods and adjusting for study imperfections? Or is the challenge more in the communication of the assumptions and limitations in the context of the imperfections? Obviously, both are important as you've well presented, but any thoughts on preference or focus on one over the other as it relates to integrating our work with other complementary disciplines? So more of the methods or communication of the assumptions and limitations?
Yeah, that's a good question. I mean, they're obviously both important. We certainly could do a better job in the communication. You know, as an editor-in-chief, of a relatively new journal, as we launch our 4th year of global epidemiology, we're going to start implementing something that that we wanted to do eventually, and that is to we're going to strongly encourage authors to have a lot more discussion about the assumptions that they made in the design and the analysis. So the communication part, we definitely could improve. Better communication about why, for example, why a particular model was used and why a particular dose response was used, and you know, making sure that they communicate that they understand the assumptions that are implicit in the model, and have some discussion about you know, the biological plausibility of, you know, the dose response that they used in their model, for example. So communication can certainly be improved. Well, I mean, as a methodologist, I'm a little biased that way in thinking that I think there's a lot of work still to be done on improving methods. I think we could do a better job of teaching methods as well. So both, I think, are needed.
Okay, thank you. I don't know if Igor's on or has any questions. There's one more I can read. So I'll go ahead and read it. Thanks for the good presentation. I was wondering about your take briefly on update on the epistemic development over time from Bradford Hill, 1965, and Sander Greenland, 2004, over WHO causality guidelines. Do you see a clear progression in how we infer causality? Are we better today in terms of more logical, or better today? Are we better today in terms of more logical and more logical and reasonable, in your view? And where do we need to focus on improving our causality reasoning?
Yeah, no, that's an interesting question. You know, as I was putting this presentation together, and especially looking at that slide where I listed the topics that I was going to talk about, you know, it occurred to me that, you know, somebody could kind of think of my list of topics as, you know, Bradford Hill 2.0, as, you know, he had a list of considerations, and this is my list of considerations, and of course they're very, very different. But in some sense, the purpose is similar, which is to how can we better get a better sense of what is a cause or not. So I don't know that we're so the problem with Bradford Hill is that it's so qualitative, and it doesn't lend itself. So when do you know if it's a cause or not? You know, you can do a so-called, you know, Bradford Hill analysis, which I've seen a few people say sometimes, which doesn't make a lot of sense to me, because there's really not an analysis going on here. But one of the limitations of Bradford Hill is that you can't say, okay, given this, this, and this, it's a cause, because it seems like, you know, when people do a so-called Bradford Hill analysis, especially if they're legal consultants, they are going to use Bradford Hill to say that there is or is not a cause based on what their bias is, and it can be easily used that way, it seems to me. So So the purpose of what I put together is to try to move us forward from that qualitative to something that's more grounded in philosophy and logic and more quantitative, where we can more definitely say, okay, given these considerations, it's likely that we have a cause. So I think we're not yet too much better than Bradford Hill, but I'm trying for us to be better than that.
Okay, thank you. I guess we only have a few minutes left. I don't see another question, but I will kind of ask one. You again, you spoke a little bit earlier about your the journal, your editor of Global Epidemiology. Are there specific things that you're interested in? I've looked at the kind of the page on the website. Are there, you talk specifically about interested in things that kind of relook at things with bias analysis, methodological developments. Do you want to say any more about, I guess, in the last couple minutes or so, about the kinds of articles you're particularly interested in global epidemiology, and what your focuses might be?
Sure. It looks like we've my webcam has been turned off by the organizer, but I can still answer your question.
I can give it back to you.
Okay.
That's her signal. We're getting close to the time, but maybe that'll be the last question.
Do I need to show my screen? I don't know. Anyway, I don't.
We see your screen. Yeah.
Okay. So, you know, Global Epidemiology is an international global health journal, but it's also, so it has two purposes. One is international health, to publish papers on international epidemiology studies, but we're also, one of our pillars is also methodological studies. And our focus is on not so much the statistical type methods papers. We're interested in philosophical and logical concepts that underpin epidemiologic methods. So that's how we are different methodologically from other journals. But we are very much interested in things like what I've been talking about today: philosophy and logic, the fundamental underpinnings of epidemiologic methods, study design, conduct, and analysis. So yeah, and papers like that, either a new methodological development for these philosophical and logical issues, or teaching papers that do a better job than current textbooks on teaching these fundamental issues, we're very much interested in.
Great. Okay, thank you. So it's precisely 2. I'll just turn it over to Sandrine to close this out. Thank you very much for a very interesting presentation, Dr.
Yeah, my pleasure. Thank you.
Okay.
Okay.
Sandrine. Yep.
Thank you, Dr. Maldonado, for this great and engaging presentation. I also want to thank our audience for joining us today and for your questions. I am trying to share my screen. It doesn't seem to be working, unfortunately. I have one more slide to show. There you go. Just so that you can see our HESI website. So we will be taking a break over the holidays with this webinar series, but we will resume them in 2022. So we hope that you will join us in the new year. And so once again, if you have any questions or comments, or if you would like to suggest any speakers to us, please send me a note. And also any feedback on these webinars would be welcome. So do not hesitate to contact me. And likewise, if you would like any information on our Environmental Epidemiology Committee, please contact me and we can have a conversation and I can update you on what we have been doing. So for now, I'm going to thank Dr. Maldonado again. Thank you for your time. And thanks everyone. And I wish everyone a happy holiday season, and hopefully we'll see you and talk to you next year. So bye everyone.
Okay. Thank you very much. Bye-bye.